Yes. How are you? Good morning. Now today we will study about hydraulic jump. In labor language or a common man language, hydraulic jump means water jumps from lower elevation to higher elevation. But as we are engineers and you are all engineering students, we should speak in terms of technical terms. For that, you refer to this figure. Consider the flow of water over a dam as shown in this figure. The height of water at the section 1-1 is small. As we move towards the downstream, the height or depth of water increases, that is shown in section 2-2. This increase is rapid over a short length of the channel. The length between the section 1-1 and 2-2 is very small length, you can see here. This is because at the section 1-1 the flow is a shooting flow, that is supercritical flow, as the depth of water at section 1-1 is less than the critical depth. Shooting flow is an unstable type of flow and does not continue on the downstream side. Then this shooting flow will convert itself into a streaming or tranquil flow, and hence depth of water will increase. The depth of water will increase. That can be seen here. The depth at section 1-1 is very low, whereas depth at section 2-2 is much higher. This sudden increase of depth of water is called hydraulic jump or a standing wave. Standing wave is nothing but known as stand still. Stand still. Now you look at the same figure which was shown there. The hydraulic jump is accompanied by rollers as shown here. It is accompanied by rollers. This is supercritical flow here, and then it jumps to become subcritical flow. Here it is supercritical flow. That means we can define in the other way that hydraulic jump is the one which transforms from supercritical to subcritical flow. Supercritical is nothing but shooting flow, whereas subcritical is tranquil flow or streaming flow. The hydraulic jump is defined as the rise of water level which takes place due to transformation of the unstable shooting flow. Unstable shooting flow, that is supercritical, as I have already said, to the stable streaming flow, that is nothing but subcritical flow. When hydraulic jump occurs, a loss of energy due to eddy formation and turbulence flow occurs. There will be loss of energy. Supercritical flow as shown here in the figure when Faraday number is greater than 1. Whereas subcritical flow when Faraday number is less than 1. There are two depths, D1 and D2. D1 is with respect to supercritical flow, D2 is with respect to subcritical flow, and there will be a hydraulic jump which is as shown here. Now, what are all the various locations wherein we can find the hydraulic jump? You can see here two figures are there. One figure is already seen twice. This is the third figure. The most typical cases for the location of hydraulic jump are: 1. Below control structures like weir, sluice gate, which are used in the channel. When any obstruction is found in the channel. Third location could be when a sharp change in the channel slope takes place, or even it occurs at the toe of a spillway dam. These are the various locations wherein the hydraulic jump occurs. Now, what are the effects of hydraulic jump? Actually, the hydraulic jump acts as the energy dissipator. You can see here, energy dissipator. It clears the surplus energy of water. Second effect, due to this jump, many noticeable disturbances are created in the flowing water like eddies, reverse flow, etc. Third effect, we can say that when the hydraulic jump takes place, the considerable amount of air is trapped in the water. That air can be helpful in removing the wastes in the streams that are causing pollution. One more effect that could be hydraulic jump also make the work of different hydraulic structures effective like weirs, notches and flumes. What are the uses of hydraulic jump? First of all, it is used as an energy dissipator. That means to dissipate the energy in water flowing over hydraulic structures as dams, weirs, etc. and preventing scouring. This is a good advantage. That is the use of this. Especially at downstream side, because of the velocity of flow of water, there could be scouring action that can be prevented because of dissipation of energy due to occurrence of the hydraulic jump. Second, hydraulic jump usually maintains the high water level on the downstream side. This high water level can be used for irrigation purposes. This is another important use. To indicate special flow conditions such as existence of supercritical flow or the presence of control section so that a gauging station may be located. Fourth use could be usually a hydraulic jump reverses the flow of water. This phenomenon of reverses the flow of water can be used to mix the chemicals for water purification. Means at the time of water purification, if hydraulic jump occurs, definitely it is possible to mix the chemicals very nicely. That is another good important use. Also, hydraulic jump can be used to remove the air pockets from water supply and sewage lines to prevent air locking. These are the various important uses or advantages of hydraulic jump. Now, what are the types of hydraulic jump based on Froday's number? If Fr is equal to 1, that means if Froday number is equal to 1, there is no hydraulic jump at all. If Fr value is 1 to 1.7, then we call it as undular hydraulic jump. As shown in figure here, in this figure, undular jump is irregular, not properly formed, and there are certain turbulences in water particles. Low energy dissipation, in this case, only about 5%. Second type, weak jump, when Fr is equal to 1.7 to 3. Weak jump takes place when the velocity in water is very less and the water particles cannot be stable and flows in various ways. Here you can see water is flowing in different directions. Energy dissipation is about 5 to 15%. Third type, oscillating hydraulic jump. It oscillates to and fro movement of water flow when Froday number is 2.5 to 4.5. Oscillating jump forms when an oscillating jet enter into supercritical state and the number of particles starts oscillating in clockwise or either anti-clockwise or clockwise direction, forming slighter tides or waves to the top surface. In this case, the energy dissipation is about 15 to 45%. The fourth type is steady hydraulic jump, when FR value is 4.5 to Froday's number value is 4.5 to 9. In steady jump, the bed surface is quite rough, so the particles start to tend in one direction with heavy velocity and turbulence. Frictional losses are more here, whereas energy dissipation is about 45 to 70%. Last type, strong hydraulic jump, when FR is greater than 9. Here it is oversightedly less than, but it should be greater than 9 FR value is greater than 9. We call it as strong hydraulic jump. Strong jump is a perfect jump formed when frictional losses are more and velocity is very high. You can see velocity is very high. Very high. The water changes its state from supercritical to subcritical in very shorter length when compared to all other types of hydraulic jumps. So this jump is highly preferred in dam structures. The energy dissipation is about 70 to 85%. These are the 5 types. Therefore, classification of hydraulic jump or types of hydraulic jump, we can say FR1 is less than 1, jump is impossible, violate second law of thermodynamics. FR1, that is Froday number is 1 to 1.7, already said standing wave or undular jump, about 4 times y too long. Low dissipation of energy, that is less than 5%. When FR is equal to 1.7 to 2.5, smooth surface arise with small rollers known as a weak jump. Dissipation is about 5 to 15%. If FR is equal to 2.5 to 4.5, which is unstable, oscillating jump, each regular pulsation creates a large wave which can travel downstream for miles together, damaging earth banks and other structures. Not recommended for the design conditions. Dissipation of energy is 15 to 45%. When FR1 is 4.5 to 9, stable, well balanced, steady jump, best performance and action intensive to downstream conditions, best design range, dissipation is about 45 to 70%. Whereas if Froday number is greater than 9, rough, somewhat intermittent, strong jump, but good performance. Dissipation of energy is 70 to 85%. Assumptions in the hydraulic jump. What are all the assumptions being done so as to determine the hydraulic jump? The channel is horizontal or has very small mild slope, so that the component of the weight of the fluid in the direction of flow is negligibly small. Second assumption, the flow of water before and after jump is uniform and one-dimensional, and therefore alpha and beta is equal to 1. What is alpha and beta? Alpha and beta, correction factors. The pressure distribution follows law of hydrostatic before and after the jump. Jump takes place at very short length of channel section and therefore loses due to friction on the surface of the bed of channel are small and hence neglected. So losses due to friction is neglected. Component of the weight of the fluid in the direction of flow is negligibly small. Alpha and beta, that is correction factors, assumed to be 1. Pressure distribution before and after the jump will remain same. Now expression for hydraulic jump. So let us consider two sections as shown here, 1-1 and 2-2. Let it be H1 or Y1 or D1. In different books the height of flow in the channel is taken as H1 or Y1 or D1. Similarly at section 2 to H2, D2 or Y2. Let us see. Let D1 depth of flow at section 1-1. Similarly D2 at depth of flow section 2-2. V1, V2 are the velocities of flow at section 1-1 and 2-2 respectively. Z1 and Z2 are the depth of centroid of area of section 1-1 below free surface. A1 is equal to area of cross section at section 1-1 and A2 is area of cross section at section 2-2. Also consider unit width of the channel, that is B is equal to 1. B is equal to 1. That means unit width of channel. Next, the forces acting on the mass of water between section 1-1 and section 2-2 are pressure force P1 on the section 1-1, pressure force P2 on section 2-2. Second force is frictional force on the floor of the channel and weight component, which is assumed to be negligible. Let us assume small q is equal to discharge per unit width. That will be equal to, therefore, V1 D1 is equal to V2 D2. Let us call that equation as 1. Now, pressure force P1 on section 1-1 is equal to rho g A1 Z1, that is equal to rho g D1 multiplied by 1 is nothing but area, and Z1 is nothing but D1 by 2. Therefore, this works out to be equal to rho g D1 squared by 2. Similarly, at section 2-2, rho g D2 squared by 2. Net force acting on the mass of water between sections 1-1 and 2-2 can be taken equal to rho g D2 squared by 2 minus rho g D1 squared by 2 is equal to rho g upon 2 whole multiplied by D2 squared minus D1 squared. Let us call this equation as 2. But from the momentum principle, we know that the net force acting on a mass of fluid must be equal to the rate of change of momentum in the same direction. Rate of change of momentum in the direction of the force is given by mass flow rate of water multiplied by change of velocity in the direction of force. Therefore, mass of water per second is given by rho multiplied by discharge per unit width multiplied by width. Therefore, rho q1 is equal to rho q meter cube per second. Here width is considered as unit width. Change of velocity in the direction of the force is given by V1 minus V2. Therefore, rate of change of momentum in the direction of the force is equal to rho q V1 minus V2. Let us call this equation as 3. Further, therefore, according to the Newton's second law of motion, as we have already stated there, equation 2 will become equal to equation 3. Therefore, rho g by 2 multiplied by d2 squared minus d1 squared must be equal to rho q v1 minus v2. Further, but from equation 1, v1 is equal to small q upon d1 and v2 is equal to small q upon d2. Further, if you simplify the equation, we will get rho g by 2 whole multiplied by d2 squared minus d1 squared is equal to rho q whole multiplied by small q divided by d1 minus small q by d2. Therefore, further if you simplify, rho g by 2, this row and this row will goes away, left with g by 2 d2 plus d1 multiplied by d2 minus d1. You can write, you have learned in mathematics, a plus b into a minus b is equal to a squared minus b squared is equal to q squared whole multiplied by d2 minus d1 divided by d1 d2. Now g by 2 d2 plus d1 is equal to q squared divided by d1 d2, or d2 plus d1 is equal to 2q squared divided by g d1 d2. This g should come here. 2q squared divided by g d1 d2. Okay, you have to make a correction in this formula. Here g also will come. This g will come to the right hand side denominator. Multiplying both sides by d2, we get d2 squared plus d1 d2 is equal to 2q squared divided by g d1, or d2 squared plus d1 d2 minus 2q squared by g d1 is equal to 0. Let us call this equation as 5. Now equation 5 is in quadratic equation in d2, and hence its solution equal to d2 is equal to minus b plus or minus square root of b squared minus 4ac divided by 2a. That is the solution to quadratic equation. You will get two roots here, means two solutions, out of which negative root cannot be possible. Only positive value you have to take. That will become equal to d2 is equal to minus d1 by 2 plus under the root d2 squared by 4 plus 2q squared by gd1. Here, equation 6. If you simplify this further by substituting the value q1 is equal to v1 d1, then d2 you will get d1 by 2 plus minus d1 by 2 plus under the root d1 squared by 4 plus 2 multiplied by v1 d1 squared divided by gd1. Here this d1 goes away with the square. Therefore, d2 is equal to minus d1 by 2 plus under the root d1 squared by 4 plus 2v1 squared d2 divided by d1 divided by g. Similarly, you can obtain the value for d1. Then depth of hydraulic jump is equal to d2 minus d1. It is here. Hydraulic jump is equal to d2 minus d1. After you find out d2 and d1, this is the derivation for hydraulic jump or expression for hydraulic jump. Are you followed? Fine. This is the hydraulic formula. Whatever we have done so far, that is just as a summary it is given, where d1 is the initial depth and d2 is called the conjugate depth. Both are called conjugate depths, are also known as conjugate of each others. Also it is known as subsequent depth. Hydraulic jump, loss of energy, that is not quite possible in this class. Just HL is equal to E1 minus E2 is equal to D2 minus D1 cube divided by 4 D1 D2. And length of jump, usually it cannot be calculated because the point of occurrence and point of ending of hydraulic jump cannot be predicted. Practically it is quite impossible to find out exactly the length of jump. However, by experience, as a thumb rule, it has been decided and it has been suggested to take 5 to 7 times of d2 minus d1. That is nothing but hydraulic jump. Height of hydraulic jump is equal to d2 minus d1. Length of hydraulic jump capital L is equal to 5 to 7 times hydraulic jump. The difference of depths before and after the jump is known as height of jump. Okay, we'll stop here. We'll continue in the next class. Thanking you. The same reference books, Subramanya, P. N. Modi and Seth, R. K. Rajput and R. K. Bansal. You can use it and study, practice the derivations, so that definitely it is possible by you to understand much better. We'll stop here, continue in the next class. ಬರ್ತಾನೆ ಇಲ್ವಲ್ಲಪ್ಪ.